Okay, well, we are going to kick off Fuseology, and this is a session, a 2-hour session that we will be focusing on fuses, how they work, how they function, how they do what they do best, and hopefully what we'll take out of this is a good overview on how to pick the right fuse for the job to get done at hand. So let's get this let's get through the details here just with regard to setting everything up. Again, everybody who is on WebEx, your phones have been muted. Please, you guys have done a great job over the last week, 2 weeks. I know we've had a little rocky start together, but everybody is being mindful of that mute button. Sometimes we accidentally hit it. Please just keep your eyes on it. Don't make those accidents happen, because I'll have to find you and shut you down, and I will call you out once I figure out who it is. So make sure we stay on mute. The guys on YouTube land, you don't have to worry about that. My obligatory thing, I am although I am a code making panel member on 2 and 10 and I sit on other NFPA committees, I am not speaking on behalf of NFPA or any of the committees. I'm speaking on behalf of myself. These are my opinions alone. We all have opinions, and I am just going to give you mine, and you have the chat windows to give me your opinions. Please do so. That would be great feedback on any areas where you disagree with me. Remember, believe half of what you hear and less of what you see. So always question often. So I don't want to show that yet, because what I want to do now is I'm going to go back. And somewhere on my desktop, I have the quiz questions. And I will say that I'm very proud of everybody, because you guys and gals did a great job in answering these questions. You got a lot of the questions right. And no complaints from my end of the world. I just got to get to the beginning to make sure that maybe I made this quiz a little bit too easy, but I think what you may take away from all of this is that in many ways, the fuse can make your life a lot easier, just because of some of the fundamental principles and the physics behind these devices. And let's walk through it. All fuses are current limiting. Now, we only had 128 respondents, which is fine. That's good. Thank you for jumping in. And if you still want to participate in this quiz, which is separate from sign-in numbers, it's 315894. You can go, if you haven't seen this, you can go up to your browser, open up a second little window, and go to menti.com, type in 315894, and you can participate in this. This does not have your name and anything associated. This is anonymous. And basically, this helps me understand where your head's at with regard to the technology that we're going to be talking about and the topics that we're going to be talking about. And these are always good, thought-provoking things. So and this, remember, this has nothing to do with the PDHs. This is nothing to do with sign-in. This is separate. All fuses are current limiting, true or false. And the right answer on this one is false, because not all fuses are current limiting. There are some fuses that are non-current limiting. We will talk about those. We will show you the trip curves for those to help you understand what we're talking about in that regard. And we will be talking about where you would typically see those in the systems. So the right answer for this is 109 false. And those two that aren't sure, thanks for playing the game, and hopefully you are in either TubeLand or on WebEx, and you're going to learn something today. So the answer to that one is false. I would use the following fuse on a transformer primary: fast-acting fuse, not sure, and time delay fuse. The right answer for there is a time delay fuse, because when you think about, just think of the words time delay. I mean, fast acting, time delay. Think about a transformer. What happens when you energize a transformer? You will draw inrush currents, and you don't want to open that overcurrent protective device on inrush currents. So it's really critical that we understand how to pick the right fuse for the job. I think out of anything that would be probably something that would be a challenge if you've never specified fuses, if you've never worked with fuses, just the sheer number of types of fuses that you have to pick from can make it a little, probably a little challenging, and that would be probably the most complicated aspect of applying fuses, would be picking the right fuse for the job. And by the end of today's 2-hour session, you guys and gals are going to be pros. So you 11 that aren't sure, thanks for showing up. And the ones who said time delay fuse, you got the right answer. So go to the next one. A clearing time of 0.07 seconds will be the same for all class fuses, but may not be the same between manufacturers. We have 32 trues, 94 falses, 95 falses, 33 not sures. Now, let's ask why 0.07 seconds. Well, if you were in some of the classes for the code changes, I think one of the earlier ones, if you were in my hazardous or arc flash, I did 2 sessions on incident energy reduction. 240.67 is a new requirement in the National Electrical Code. It was new in the 17 code with an enforcement date of January 1st, 2020. And 0.07 seconds is a key number that you have to have a clearing time of 0.07 seconds or faster at the arcing current to meet that section of the code and not require an additional arc reduction technology. And the message here, the 99 who have said false are in the right bucket. And the reason is because, and you're going to learn that even though I have a 100 amp or I have a 1200 amp fuse, remember it's 1200 amps and above, I have a 1200 amp fuse, the different types of fuses, whichever, whether it be a different manufacturer or different model numbers within a single manufacturer, the trip curves are going to be different. So that 0.07 second clearing time for one fuse model and manufacturer is not going to be the same for a different fuse model and manufacturer. All right. You're looking good so far. I mean, these are great. Look how we have 107 say false, and if they're right, then we've got 108 people that think they're right, which is good. And we only have 39. So to achieve selective coordination for any fuse, all I have to do is maintain a 2-to-1 ratio. And the right answer to this is false, because some fuses may need a higher ratio than 2-to-1. You've got to understand the selective coordination tables. And I do have, and I had a slide right before I put this up, but this is a fuse ratio tables, and what you'll notice here, oops, I'm fumbling on my side of the table here, but I'm going to do something. You'll notice that the way they lay out, the fuse guys lay out their tables, they have the downstream fuse across the top. So these fuses here are the downstream fuses, and these fuses over here are the upstream fuses. So that in a system, when I say downstream and upstream, so I have a fuse feeding a fuse, and say this is the load. Okay, that fuse is up top. I'm sorry, that fuse is down here on this side. This fuse is up top. Now, if I've completely confused you, then I've done my job. So the downstream fuse is across the top. The upstream fuse is down the side. So what you would do for any one of these, if you'll notice the 2-to-1 ratios, okay, on the LPJs, on the TCFs, on the LPN and the LPSs, okay, these are 2-to-1 ratios. Somebody's unmuted themselves. Or Priby. I'm going to find you, buddy. So you'll see there's some 8-to-1. There you are, and you are muted. There are some 8-to-1s in here. There are some 4-to-1 ratios, depending upon what you have upstream and downstream. Now, if you use a specific, if you just jump into a certain type of fuse, class or family, then you're pretty much safe. But just keep in mind that these tables for fuses, just not every fuse is 2 to 1. You do have to be mindful that is not the case. So the right answer here is false. So 122 of you can stand up from your chair, pat yourself on the back, turn around 3 times, and sit back down. Thank you very much. So if I write my specification around fuses, I'm tied into only one manufacturer, and that is false, which looks like the majority of you know, except for that one person who doesn't even know who they are. It is over there on the, and we love you too. So the key thing, remember, usually when you'll see a specification or equipment, it'll tell you a class J, class L, class T fuses, and they'll tell you the size. Because of the nature of how we list these devices and how we make products, any of the 3 manufacturers out there, you can put their fuse in those holders, but I know who you're going to pick. But in any case, you can put any fuse in those holders because they're really built around the class fuse, and the class designation of a fuse will dictate the size of that fuse and how it's mounted, so that any fusible switch or any holder that will accept a certain class, you know that any one of the manufacturers who make a fuse, you can fit in that hole. But again, I know who you're going to pick. David Engelhardt. So the clearing time of 0.07 seconds is true. That is the 0.07 second question. The answer was false, because every fuse curve is probably going to be different, especially if it's different between manufacturers. All right. Hopefully that answered your question. And the right answer on this one is, again, false, because of the reasons I just said. You can put, if you wrote a spec around a fuse, you automatically meet 3 manufacturers would be able to quote that job very easily. So you have to be careful when installing fuses to ensure you don't put a lower interrupting rating fuse in place of one that is supposed to be higher, or higher. That's a new word. I got to put that in my dictionary. Hgiher. Was supposed to be higher. So the good thing about fuses as well is they have rejection features, so that you can reject the voltage, you can reject on current limiting and interrupting ratings. So that's a very nice feature of fuses. It helps make, even in the installations, makes it easier and a little bit more foolproof, because they do have the ability to reject when you make it a lot more difficult to screw up the installation in the field. So that's another nice thing of these fuses. I would say that false is actually the right answer here, because I have the rejection features on fuses that help prevent a mistake in the field. I don't necessarily have that on circuit breakers, but I do have that on fuses. So I can use up, over, and down to establish protection of busway. And this is, I use the term up, over, and down. I could say the current let-through curves. That may have made this a little bit easier. And maybe I could have gotten a few of those 78 that said what's up, over, and down over into either the true or false. So we're going to talk about this too. And yes, you can use the current let-through from the current limiting devices that curve the current let-through tables and curves to be able to show that you can protect busway and provide, because it's a static device. I can't necessarily do that with, that's Cernco spelling. I can't necessarily do that with a dynamic device like a circuit breaker, but I can do it on static type devices like busway, cables, and other similar things that aren't trying to open the circuit at the same time that the fuse is trying to open the circuit. So the right answer here is true, those 62. And we're going to talk about this in a little bit more detail, and I'll give you some good reference information to put into your library, either your electronic library or your physical library. All right, 24067 requirements will impact the following Well, it almost looked like I misspelled following, but I didn't. The following fuse classes, select all. We have class H, class L, RK1s, RK5s. Okay, what are you talking about here? 58 of you. And I can tell because all of this is spread out all over the place. What you'll, the key thing to remember, 24067 impacts all fuses 1200 amps and above. So a lot of the fuses that I have listed there, especially the CCs, the Charlie Chaplins, don't go above 30 amps. So it definitely would not impact the CC fuse. The Class T fuse, I believe we do make, the largest Class T fuse is a 1200 amp fuse, so that could be impacted. The Class Ls, definitely, those are big boys. L is for large. And we're going to go through each of these classes. Class L and Class T are the two big ones in that list. The rest don't go up to 1200 amps and above. Your Class L, that's going to be, when you see a Class L fuse, that's the workhorse of your very large 1200 amps and above type of installation. So I could tell we've got some learning to do with regard to the system. So I saw a question from what about when a busway has a plug-in switches, which OCPDs with overcurrent protected devices is no longer just a passive busway. As long as Jeff Ectos, so Jeff, as long as I'm not trying to say I'm increasing the short circuit, the interrupting rating capabilities of those breakers, but I can say I'm protecting the busway because it is a static device. I just can't claim that I am providing protection for the circuit breakers. David, I'm gonna have to mute you, David. Where are you at, David? There you are. You are done, and I'm calling you out. Gotcha. All right. Sorry, everybody. Yes. What do the other fuse class letters represent? Well, we are going to get into that here in a second after we get through the quiz. My favorite football team is, and looks like we've got a lot of Steeler fans out there, 151. I'm sure 100. Well, we got more than 153. We've got some multiple choices there. People picked multiple, so we got 100. We got over 200 respondents. So it looks like we've got a lot of people that just love the Steelers, and you know what? I kind of thought that. All right. I think that was the last question. Okay. Thank you for playing the game. And now we are going to go to our regularly scheduled program. And we're going to start talking about the fuse. Okay. So the fuse. The fuse is defined in Article 100. And basically it's going to open. It's going to sever the circuit in some form or fashion by heating an element that's inside. It is not reusable once you've spent that fuse. We do not say blown fuses. We say opened fuses. And I know our fuse guys are sensitive in that regard. So I know we probably have a few of them on the phone. So we'll treat them well. A fuse comprises all of the parts that form a unit capable of performing these functions. So the fuse does not necessarily include the holder, right? Now, some of these are bolted into place, like your big Class Ls are bolted into place in the equipment. Go Lions, go Titans, come on. So a fuse comprises all the parts that form a unit capable of performing the prescribed functions, and again, it may or may not include everything that's necessary to put that into the circuit, and that's specifically speaking to the holders themselves. We don't include those holders, but a lot of these are just bolted into place. Alrighty then. The UL standards that we use, UL 248, low voltage fuses. We're going to talk about all the different, there's like 15 different standard parts to that. But this establishes the performance criteria and all of the acceptance criteria, from a fuse and a holder 248 is the fuse, 4248 are the fuse holders. And they work hand in hand, because once we have a fuse class, that will define the dimensions of that fuse, and that tells us in 4248 the holders and how to make those and the dimensions. So they relate very closely with each other. But those are the two standards for the fuse themselves and the holders. If I look at UL 248, I have .1 is general requirements, very similar to the NEC. They'll have general requirements that apply generally. And then there are specifics for each of the classes of fuses, because each of these fuses will have different sizes. They will have different types of rejection features and things like that, and different performance capabilities. So, and how we test these, we establish in 248 all of the criteria that these fuses need to pass. And this is not going to be meant as a UL standard educational class, but this is basically to let you know that UL 248 is the standard. And if you see a 248-5 or -12, those are the specific classes of fuses. All right. And then the same thing goes for the fuse holders, because if I have a CC fuse, I need a CC fuse holder, and there will be specific requirements that each of these, because of the dimensions and whatnot of each of the fuse classes, you'll have different parts of the standard. So this is the way the standards are laid out for low voltage fuses. All right, those are the standards. Now your basics. Again, you have a fusible link, or there's multiple links that are, and we say in a tube. It doesn't necessarily have to be a tube. As you'll see, there are some fuses that are in this little square blocks. We have some people that think out of the box and don't just put fuses in tubes. So there are different ways that the form factor may be different. Just like a circuit breaker or any type of device you put in the circuit, there will be a resistance and impedance to that. The elements and the contacts and whatnot. Breakers have contacts. Fuses will have the element, and you'll see both fuses and breakers, they'll be warm. If you put a whoa man, I'm having a hard time. Thermography or whatever. I have a hard time with that word. There's electronic devices that sense temperature without touching it. And even the ones that do touch it, you'll see that these devices get warm, especially when they do their job. They can have single elements or dual elements. We'll talk a little bit about that as well to help you understand how that develops the curve. And then again, what happens during an overcurrent condition, and we'll show you some pictures of spent fuses, some opened fuses, and how they isolate the currents, and we're going to talk about that fuse element. Now, just like in many overcurrent protective devices, you have lots of options. You've got the class CC, the Charlie Chaplins of the world, and the reason we call it Charlie Chaplin, and this is Cernco class 101. Timmy taught me this one. You see this little nub right up here? It looks just like Charlie Chaplin's hat, if you know who Charlie Chaplin is. Or you can call it control circuit. These are what you see on those little transformers that you'll have in industrial power systems, where you have a little control power transformer type of deal. These CC fuses, you'll see that there. They only go up to 30 amps. So you'll notice, again, you'll have an overlap. This goes up to 30 amps. Obviously, I can get a class CF in 30 amps. I can get a class G in 30 amps. I can obviously get a RK1 in 30 amps on RK. So I can get a 30 amps in any one of these fuses. And the big question you should have in your mind is, how do I know which fuse to use? And hey, that rhymed. How do I know which fuse to use? We can make a song. You have to understand the characteristics. And whenever for me, the time current characteristic curve for me is the determining factor. And if you look at any one of these examples, like for example, the CC, a very small, fast-acting single-element fuse for protection of branch circuits, motor control circuits, lighting ballasts, they may be fast-acting, but they've got to have some sort of delay in there to be able to be used on those circuits. And the trip curve should reflect that. And we're going to hopefully look at one of those trip curves. The class CF, Again, small installed footprint. That was basically a Class J fuse performance put into a different footprint so that we can make a panel board that could be used in all of these that is a much smaller footprint, smallest in the industry, and could be used as a panel board in, say, Article 700 systems, et cetera, or data centers, things like that. And also industrial control panels use Class CF fuses. They're a nice finger-safe solution. And then you have your Class Gs. It's a branch circuit fuse for lighting, appliances, and motor branch circuits. Only goes up to 60 amps. The RK1s, RK5s, there's probably a lot of people on the phone that know, oh yeah, I use those RKs a lot. And we'll look at the trip curves. And we'll compare the RK1 with the RK5 and the Class J, which will basically be the same as the Class CF. I think I took a 100 amp fuse to show the differences in those. And because really in my mind, when I think of RK1s, RK5s, and Js and whatnot, I'm picturing fuse curves because that's really what it's all about. It's about the current limitation, but Roger, good point. But it is about the performance of that curve. So Roger pointed out a good, interesting point, and I'm going to go back. I'm going to go back in time. Article 100 fuse. Roger Zieg. Yes, you pointed out, and I'm an area that I thought was very intriguing recently, and I'm making a public input on this one as well for the 2023 cycle. Fuse is defined in Article 100. It's defined in Part 2. So to find the definition of a fuse, you have to go to Part 2, which is, let me make sure it's Part 2. Yep, Part 2, over 1,000 volts. And so, which, if you look at in Part 2, oops, somebody just took themselves off mute. Thank you for putting yourself back on mute. The definition, unfortunately, for fuses in the medium voltage is in over 1,000 volts nominal, Part 2, not in Part 1. And everybody, every fuse manufacturer, every presentation that I have seen people put this together, they always go to Part 2, never ask that question, sort of like I did here. So, Roger, you get brownie points because we are going to have to probably make a change to the NEC to pull that definition, either leave it in Part 2, but then also make one in Part 1, which I've created some language, and I've already submitted that public input for the 2023 cycle because, to your point, there is no definition in Article 100 Part 1. There is in Article 100 Part 2 for medium voltage. A little factoid that you might have found interesting. So I diverged, and now I am back on track. Class, so we're going to walk through to help you in the way I look at things. Everybody's different. I'm going to show you my perspective on understanding all the different fuse classes and how I would determine when to use these devices and which device I would pick. So in any case, let's and you'll see the Class L's go up to 6,000 amps. They start at 601. So remember that one question I said, which one of these class fuses are impacted by 24067? Class T goes up to 1,200. That's the upper limit. So that one's impacted because 24067 only applies to fuses 1,200 amps and above. If I have a Class T 1,200 amp fuse, I am into 24067. Class L goes from 601 to 6,000. That's the sweet spot of those big fuses that you'll probably see. But when you look at the curve of the Class T, you're going to fall in love. It's going to be a magical moment. So I want you to prepare for that. If you ever heard of love at first sight, it's the Class T. T is for tiny. Wait till we get into that. Now, high-speed fuses. When I first started working at Bussmann I moved over to the Busman Group back, I'd say about 6 years ago or something like that. I've been with Eaton for 24, 25, since 1995, however many years that's been. But I never knew what the heck a high-speed fuse was until I moved over there, because I never really got into the application of a high-speed fuse, because high-speed fuses are really used inside of equipment like variable frequency drives and things like that. And an interesting thing I learned about high-speed fuses, I'm used to the world of these fuses, where what do? We do a load calculation. We figure out what the ampacity and what size conductor I need to use. And then once I know the conductor and the size of the conductor, then I go to 310 15B or 310 16, and then I find my overcurrent protective device size that will protect that conductor. That is not how we do things in the high-speed fuse world, because when you're applying a high-speed fuse, you're looking at the I squared T let through, how much energy you are going to let into the system. That's how they determine what high-speed fuse to select. That was an interesting thing. I sat on the help desk for a while, and that's when you really learn, is when you're taking 800 number calls and you're trying to help people pick the right fuses. That's when I really learned a lot about high-speed fuses. And that is short circuit protection, ground fault protection, etc. Again, power electronic drives. This is going to reduce the damage inside. They are very fast-acting devices. So, Mr. Mark Goldstein, if you'll probably scroll up on YouTube and see the code. You need to sign in at the Mentimeter. Go to menti.com, and there's a 6-digit code that you need to plug in, and I'm sure somebody on YouTube has posted that number. So scroll on up. If nobody has, please post that for Mr. Mark Goldstein, or Goldstein, whatever. Hopefully I didn't say your name wrong. Alrighty. And then there are supplementary fuses. Just like there are supplementary circuit breakers, there are supplementary fuses. And I believe somebody at one point told me that I asked them, what's a supplementary fuse? And they said it's a fuse you use when you don't need a fuse, which I thought was very interesting. But these devices are not branch circuit rated. You can't use them to protect a branch circuit. This is where supplementary overcurrent protection in things like luminaires, appliances, you'll see these inside of equipment and any type of like little panels and whatnot. You'll see your HVAC unit. I just had to, I think it was last year, I had to replace a fuse. We had a huge event outside, a lot of lightning and whatnot, and I had a surge that opened up a fuse. So I had to replace one of those, but that would be a supplementary fuse. Go to menti.com, Mr. Mark, www.m as in Mary, enti.com. Okay, so that's your supplementary, and we have supplementary circuit breakers. We'll have supplementary fuses. You know, these, they all work alike. Dual element time delays. You'll actually see this in the National Electrical Code. If you look at, what's the article on motors, 430? Yep, 430 on motors, 430.52 talks about dual element time delay fuses and then non-time delay fuses when you're talking about motors. And if you ever wondered what the heck is a dual element time delay fuse, these are modern fuses, current limiting in nature. They are basically designed, and I'll show you, it really gets back to the trip curve. I mean, I'm a TCC, time current characteristic kind of guy, and that's really where you'll see the benefit of a dual element time delay fuse. Again, you'll see these on motors and transformers because they provide very good short circuit protection, but yet they let the equipment start. If it's a transformer, they'll let it energize. If it's a motor, they're going to let it start. So you have an overload, time delay element, and a short circuit. And when you open one up, this is what you see. You're going to see an element that has a bunch of pinch points. And then you're going to have another element that looks like it has a little solder like a little silver unit to it, and I think the cube fuse, um, the cube fuse is and I laugh because it has it has like, it almost looks like a little piece of chewing gum sitting in there, and it's just a portion of it that helps it and gives you the long time thermal capabilities because you're melting something. And basically, in that little part, you have a little nub that's spring loaded. It's connected by a very tiny pin, I would call it, that when it melts, it opens and clears the fault. And that is, again, that's a long time delay. But anytime you hear of, like in circuit breakers, you'll have a bimetal in there that will bend, slowly bend, because as it gets hotter, it will start to bend. But as a fuse, you're not bending anything. You're going to slowly melt something because it's all about the physics of heating and the metals that are selected there to melt, and then it opens on the long, persistent overcurrents. So you have the overload element, which is identified where it's pointed. I don't have to draw anything. And then you have the short circuit element, which has all of those small pinch points that basically, under very high fault currents, those little pinch points, and remember, what I'm not showing here is that there's sand all around this. And what happens is all of those pinch points basically explode. They heat, and the sand, I mean, you think about it, when sand gets really hot, what happens? It turns into glass. We call it fulgurite. I don't mean to get vulgar with you, but it's called fulgurite, and it will basically insulate and isolate the circuit, basically stopping the flow of very high fault currents. And when one is actually done, this is a picture of a fuse. So you notice that the previous photo is pretty accurate in what this thing looks like. So you see all of the pinch points were basically in here. These were that square element, right? And this is where that overload region is, right? We saw, and you'll notice there's two elements in here, not just one. And it's a dual element type of device. And these bear the brunt of the short circuit. And if I took one of those out and said, what does it look like brand new? This is what it would look like brand new. So here's your flat part. There's your flat part. So if I counted 1, 2, 3, 4, 1, 2, 3, and then 4, and then you're getting into this end over here, which is where your thermal capabilities are, and this end is over on this side. So that's what's on the inside of these breakers, or I'm sorry, inside of these fuses. I have OCPD issues. Sometimes I argue with myself, but it's okay. I got fuses on one shoulder, breakers on the other, but I know I'm in good company in both cases. So these little pinch points right in here, that's what does the high current short circuit. It turns that sand into fulgurite, creates and isolates the system. And if an interesting fact, if you were ever wondering, if you've opened a few fuses and you're not sure why and how much current you're really drawing because you don't have it metered or whatnot, then you could x-ray these and see how many of these pinch points have cleared that fault, or maybe just this opened. And by knowing those little details, our scientists at Bussmann can tell you approximately how much current was flowing through that device when it opened. Now, this is when it gets real in my ballpark, because relating that element to the trip curve of a fuse is when you really understand the benefit and the values of these things. So this overload area is all up in here, and there's a point when on this curve that you start to hit these pinch points, and it's probably somewhere in this region and to the right. But this curve is built off of that element, and every fuse is a little different, and the requirements from a UL standpoint is a little different, and we have to make sure that we design these fuses to not open on things like transformer inrush or motor starting currents, those currents that the locked rotor amps, when you first start a motor, they have to be able to live, and I need these little delays and these little humps in the system. So this area right up in here inside of that fuse is critical to help me ride through motor inrush, and we're going to show that, transformer inrush, etc. So these fuses are designed with understanding where you're probably going to apply these and what some of those data points are, like for transformer inrush and for motor starting. Right. So the element itself, it's again highly conductive material. You have low power loss during normal operation. The number of the elements and the cross-sectional area gives you your current rating. And in that one picture we showed, there were 2 elements in there for that specific fuse. I can't remember what size amp rating fuse that is. In fact, I'll tell you in a second. I'm not going to tell you in a second. I'm back. I don't have it. I think it's in the other room. I should have it here, but I don't. I used to have it here. I'm checking my, not on my table. Anyway, it's probably about 200, 250 amp fuse, something like that. And then the number of weak necks gives you the voltage rating, which I think that's an interesting thing. So if you look at this, all these little pinch points help you establish the voltage rating of that. And that's why a medium voltage, if you ever looked at a medium voltage fuse, the element inside is not straight like this, because I can do this because it's only applied at 600 volt. But when I'm applying and making a 15 kV fuse, etc., I need a lot more of these pinch points. I need a lot more of I need 1, I need 2, 3, 4. If I actually made a fuse long enough to put it straight like this, it'd probably be a few feet long. So what we do in a medium voltage fuse is we coil that inside of the fuse. It's not a straight element like this. So if you ever opened up a fuse or saw a cutaway of a medium voltage fuse, the reason is that you see that coil is because the number of those weak necks gives me my voltage rating, and I need to coil that inside the medium voltage fuse tube. So the sand fill that's inside, it has a lot of functions and features. The sand in there helps cool the fuse elements, and whenever I open that fuse, when I put a lot of current through there, I'll create fulgurite that will basically insulate and isolate the circuit once that fulgurite forms. And you saw both a created image and then an actual picture of what it looks like after one's opened. And again, the fill restricts the arcing to the controlled path. So you don't want to, you want to make sure that those little arc flash events that are happening inside of that enclosure, that tube, is controlled and held in that path. And then again, it regulates that arc voltage. So the sand plays a strategic role inside of that element, inside of that device. And then you have the body. The body is usually, it can be out of ceramic. Your high-speed fuses are ceramic, or it could be a glass fiber. Most of the RK fuses and your Class L or Class Ls, your Class H's, all that stuff is pretty much a glass fiber tube. Even your Charlie Chaplins, your CCs. And again, they have good thermal capabilities. They're a good insulator, and they conduct they conduct heat very well. and again, they can handle high temperature ranges. So, and that keeps everything together. So I know the early days, the fuse element was in open air. As they tried to do more and more, interrupt higher voltages and things like that, higher currents, they had to basically restrict that. And then the size of the fuse is driven by the class of the fuse, and the way we list these devices, there will be specific dimensions that are governed by the UL standards that tell us when we make this specific class fuse, then it has to be a certain size, and you'll have the dimensions of the length, the width, and all that good stuff. And this helps you. Remember, we had a standard for the fuse and we had a standard for the holders. So these dimensions, and there will be different dimensions for each different fuse. And you'll notice they're like the RK1s, they have those rejection features, right? And you'll notice like that on these, it's only on one side of the fuse. So every fuse is going to have rejection so that you don't put the wrong fuse in the wrong holder and put a less capable device into the wrong slot. And then you have your fuse class current limitation. So in the standards, all of the manufacturers have to meet the requirements, and they have a maximum let-through value that they're allowed for each of these fuse classes. And this is an example of the tables that are used at 50, 100, 200, and 300,000 amps. Yes, I did say 300,000 amps. Do you know we have fuses that can interrupt up to 300,000 amps? And you know what we had to do to make that happen, to make it possible for, sorry about that. What we had to do to make it possible for a fuse to interrupt 300,000 amps, we had to build a lab big enough to be able to pump 300,000 amps through it. So here's something I've said, and I said it before, and I'll say it again. Well, you know what fuses eat for breakfast, lunch, and dinner? The more of it, the more they love it, and they never gain weight. Current. They love current. They eat it up. The more you give that fuse, the more efficient, the better it's going to work for you. And in most cases, you want to feed that fuse current. You know, the whole concept of reduce your currents, reduces incident energy. If you're using fuses, you want to feed that fuse current. The more of it, the better off you are. It will act so fast. It will reduce the magnetic forces, and it will solve a lot of your arc flash and short circuit capability things, just as long as you're not working in that long time region. All right, so let's take a look. These are all 100 amp fuses, and you're going to say, wow, those are all rated 100 amps. Yes, they are. You'll notice, remember we talked about that 10,000 amp interrupting rating class H fuse, which was non-current limiting. That's this guy right over here. And when we say non-current limiting, look at the 100 amp fuse doesn't cross 0.01 seconds until way out here close to 10,000 amps. It takes a lot of current to get this device to trip in less than 0.01 seconds. The element in that fuse looks like this. Okay, so inside that fuse, this is what the element looks like. It's like one big pinch point. This is hollow in the middle, and this is your metal on either side. That's a Class H fuse. You saw what the other fuses look like. Remember, they had like that. You know, you had that going on, and you had that going on. This is the Class H fuse on the right. These are your current limiting type fuses on the left, and this is what that fuse curve looks like. It's still a 100 amp fuse, but they have a low interrupting rating. They're not current limiting. But look at all of these other nice fuses. So this is your Class T. Remember I said at love at first sight? Look at that fuse curve. It's very fast. It's moved over to the left. This is a 100 amp fuse. I still get a nice little delay in here. So if I had a motor starting curve, or if I had an inrush current, maybe this little hump will hurt me. But again, you would always want to plot this along with your motor start curve or your or your transformer inrush to make sure you're covacevic there. But in any case, there's your class H, this is your class T, and these other three, they look pretty close. And what you're looking at there, those are your RK5s and your RK1s. So your RK5 is the brown one. That's this guy right in here. The green one is your RK1. Okay, they're very similar, but you'll notice that the RK1 is a little bit further over to the right than the RK5. And maybe in here in this hump, there's a little bit of a difference. But that's, and then you have this class J. You'll look at the class J, you still get a little bit of this hump in here, but you get a little bit closer to whatever your load currents are. So, and let's take a look at if we plotted, say, a 100 horsepower motor, which the full load amps is probably around 125. So this is your motor start curve. If you've never seen a motor start curve, this is called a mistake. This is your full load amps, FLA. Boy, it's hard to write on a monitor that moves. So this is full load amps. This is locked rotor amps. So, and this transition point, this knee, really will depend upon what I'm driving, right? If I'm driving, say, a rock crusher and I have I hold those locked rotor amps because, or if I have a conveyor belt that I'm sitting on, then I will probably have it'll take me longer to get that motor up to speed. Think about something that, let's say a conveyor belt's a good example. If I turn that motor on a conveyor belt and I have that conveyor belt loaded with material, it can take a long time for me to get up the full load amps in normal running speed. But if that conveyor belt is empty, I might get to full load amps pretty doggone quick because that belt's empty and I have nothing on it. So I transition from locked rotor amps to full load amps at a much faster time than up here. So the curves, and again, for large motors is typically when we're going to be plotting damage curves or motor start curves. But if you look at these three different types of fuses, this class H fuse is a 200 amp fuse. This purple one is a 300 amp fuse. And this green one, and that's an RK1. This is an RK1. This is an H, and the green one is a J, LPJ, class J fuse. And you'll notice what the difference is between the RK1 and the class J. The RK1, my fuse curve, it takes more current to get into the current limiting region, but my class J will still let this motor start, but provide better short circuit protection because I'll go faster. I'll be further into the current limiting region because I cross 0.01 seconds with this class J at a lower current value than that RK1. And so the class J fuse probably would give you better short circuit protection for this motor, and it would still let the motor start, and would be a better performing fuse for you depending on what your goals are, whether it be price or damage, etc. Okay, so that's basically, these are all fuses that can be used on that motor. And if you look in 430, they all fall within the proper. I think the full load amps on this is 120 some amps. If it's a dual element, I can go up to 175%. If it's not a dual element, I can go up to 300%. They all fall in the window that's permitted by the National Electrical Code, but you'll notice that class J fuse is going to give me a better protection on that motor from a short circuit perspective and still let that motor start in this instance. So that's basically, that's why I say whenever I'm looking at fuses, I'm really looking at these trip curves to figure out which one I want to use in my specific application. Once you get upstream in the power distribution system, now your inrush currents aren't going to be as as large. If you think about it, you think about a one-line diagram. If I have, if you have a motor down here and you have a bunch of motors and you have fuses on these motors, right? And then they add up and you come up to uh, another set over here, and you come up to another bus, and then you have another fuse up here. This fuse, because these motors are turning on and off in different times, they're not all coming on at the same time. This fuse is not going to see as much of a drastic inrush as you would expect when you're down close to the load. So there are some general rules of which class fuse you'd want to. You may want to, if you have heavy motor loads in your system, you use a time delay fuse, something that gives you a little bit of this time delay as opposed to a fast acting fuse. But just to give you some ride through on motor inrush currents and things of that nature. But when you're down close to the loads on the primary of a transformer, right there at the motor, you're going to be considering these devices. And you can go by the rules of thumb, which will, the Busman SPD Selecting Protective Devices book is a very good resource for you in your library. And that is this book right here. I'm going to just show this one real quick. This is the Busman's Selecting Protective Device Handbook. I still have mine. When I became an engineer back in 1990, I went to an event. There was a Busman sales guy. He gave me the SPD, and I learned a lot about fuses through this book. It's a free download off the web electronically, and this one was dedicated to George Oakley. If you don't know who he is, he was a great guy with regard to codes and standards and technical capabilities. He's retired now and enjoying life with his wife. But this is a great document that goes through all of the things that we were just talked about, the construction and how they operate, how they function, all the different fuse classes, et cetera, which we're going to talk about. And it talks about the fuseology and the break and the basics of fuses and how to pick fuses. This is a must-have for your library, whether you're a fuse guy or a breaker guy, because the basic principles are still going to be the same about protection. So in any case, this is a good reference for you. I will put a link to it at the bottom of my YouTube channel. All right, so now let's go through each of the classes. The class L stands for large. But before we do that, I'm just going to go through the chat real quick. All right, I see a lot of chatting going on. You guys are chatters today. That's really good. I see I did a job where the MCC manufacturer installed fast-acting fuses on the primary of the control power transformers. Did not work out well. All right, Don. Yep. You got to be mindful of those inrush currents. That's for doggone sure. Take down the numbers. We'll start right after the tube land. Okay, I already did that. Any chance your questions can be included in professional sports teams? Code of the PDH. All right, so we saw that one. What is the definition? I'm going to move the chat over for my YouTubers out there. Just join on the call. What about busway? Okay, we already talked to that one. L stands for large. What about the other ones? We're going to get into that. Class L. What about the difference between full and AM fuses, partially in respect to using those for motors? I struggled to find the energy let-through curves for all Busman Cooper fuses for a recent discrimination study, as this will be required. Okay, what I would do, Ian, there is a email to Fuse Tech. Anytime we get questions like this, especially those high-speed fuses and whatnot, you send an email to Fuse Tech, and those guys are they are Johnny on the spot. They work 24/7, 365. They don't quit as long as you don't quit. So here is you can call a toll-free number, 855-287-7626 or 855-BUSMAN, or you can send an email to fusetech@eaton.com. They are optional. I used to manage that group. Joe Shoemaker manages that group now. They are a great team of engineers, and they have forgotten more about fuses than I probably know. Great group of guys, and they will take all of those questions. They will help you pick the right fuse for that job. You tell them what you're looking for. Even if you had one that's existing and you say, well, they don't make this anymore, some other manufacturer, you give that to them, they will do the lookup and they will find the fuse that you need. I see a lot of supplementary fuses used in industrial control circuits. Is that an appropriate use? Yeah, industrial. So as long as it's not being used as a branch circuit type of device and used in a supplementary fashion where there is an upstream overcurrent device protecting the branch circuit, etc., they can use those fuses in those applications. Usually you'll see them in an industrial control panel a lot, like HVAC equipment, things of that nature. As long as they're not being used as a branch circuit overcurrent protective device rated to protect the conductor and etc. Probably we do it where we have lots of solenoid coils. If the solenoid coil fails, it only takes out the small supplementary fuse. Yeah, there you go. Not a large branch circuit protection. Right. So, and it's a good case of, you'll use it where you don't necessarily have to because you still have that overcurrent protective device upstream. But if you have a specific reason inside of an industrial control panel that you want to isolate something, should you have a problem so you don't extend the damage beyond. I know on my Marshall JCM 1000, my 100-watt half stack amplifier for my guitar, they have a couple fuses. They have a power amp fuse, and there's another secondary secondary fuse on the board to protect the board to limit the damage to that piece of equipment. So if I have a problem, I can fix it as opposed to having to replace it. On the ones I see, fuse on each hot conductor for input devices, so a single fault does not take out the inputs to the PLC. Very good point. Yep. Is the system selectively coordinated? Joseph, no, those are not selectively coordinated, buddy. Good question. I love those jokes. Large fans can have that long start times have changed starter overloads, class 30, a number of times to permit the motor to start without tripping the overload. Yes. They have, if you have that large start fan start time, you're going to want to look for a different fuse. In fact, I had that problem on my Marshall half stack. I put a fast acting fuse in it and I would turn it on and it would open because there's a transformer in there. In the inrush current, I just could not find the right fuse for my application. Actually, I just used whatever I had in my lab. So I went down to the distributor and I got the right fuse. I will send you that link for the Bussmann SPD. I'll include that before we get off. All right, I'm gonna take a look on TubeLand and see the tubers out there and what kind of questions they've got going on. Luis Diego, I've always asked myself why the dual element fuse on transformers crosses the damage curve of the transformer, and that's how it is recommended. Yes, so remember, it'll cross the transformer damage curve, and I might plot one of those. I'm going to save that for a little bit later. Somebody's not on mute. I don't know who that is. R Prebill. I got to get you. Where are you at? R Prebill. Attendees. These. R Prebill. Oh, they are participants. I got to go down to the R's. I'm going to get you, R Prebill. I'm calling you out, buddy. RP. There you are. And you muted yourself. Look at that. Excellent. University of Texas. You are the man. All right. I will plot the transformer damage curve here, and we'll do that on my SKM, which I'm going to have to find my key. I'm going to plug it in as we speak. All right. So that was about the end of the questions over there. Now let's get back to the job here. All right. Gotta get to this, and then we need to hide the chats, and I gotta roll that down. Here we go. Class L. Class L fuses, large. These are your 601 to 6,000 amp fuses. Time delay, current limiting. You'll see these at the main service entrance equipment, large equipment, and large motors will have these. Again, when you're talking up to 6,000 amps, these are big boys. You're going to have a big load. Either it's going to be the entire facility or it's going to be a big motor. Class L, again, those are the curves. So that's what your trip curve looks like. These are average melt curves. They're not They don't have the bands on them, the plus or minus. These are just your average melt. And what I'm more interested to help you see is that you still have some distance here. You know, you have this arc, and it's not a fuse. It is not a fuse that looks like it's not a fuse that looks like this, right? Okay, it has the arch that will get you through those motor inrush currents and things of that nature in transformers. So they have a little bit of time delay built into those, but still fast acting. This is this is a class L, and look at these curves. These have a little bit different. This is the KLUs. Okay, so these have a little bit of a different just on the bottom of that curve. They still have a little nice little hump up here in this midsection, you know, but down here they've got this going on, which may or may not give you a little, but it'll act a little bit faster than the other ones. Okay, that's a current limiting fuses. T, class T is for tiny. That's how you remember. They're smaller fuses. They go up to 1200 amps, but they're not as big as those big class L fuses. They're 300 volts or 600 volts up to 1200 amps, 30, 60, 100, always up to 1200, 200,000 amp interrupting rating. Current limiting, rejection features. They got rejection features, space saving because they're smaller. You'll see these on heating and lighting circuits. You'll see these actually in residential as well, service entrance type equipment, where you want that smaller fuse performance. But remember, love at first sight. Look at those curves. Gosh darn it. They're faster. Now, you know, they probably wouldn't do so good on motors. And you know, think about a residential application, not bad. You don't have a lot of motor inrush, and heavy industrials might have a little bit trouble. But again, I love the way these things come down and it curves in like that. I think they and if you want to talk about incident energy reduction, you know, in that example that I showed you where we plotted those curves, that the class T was nice and tight to the left. Your class H, I'm not going to give this one a name. We'll just call it H. Okay, just H. Not H for anything, just H. You have the NONs, which are your 250 volts, NOS, which are 600 volts, up to 600 amps, non-time delay, non-current limiting, and I would not recommend these. You know where you'll find these HVAC equipment. You know why? Because they're the lowest cost solution. The trip curves, I plotted that trip curve. Look how they slope off to the right. They're way out there on the right. It takes a lot of current to get these puppies to go because I told you how they're constructed. They're not constructed like those other fuses. These are the ones you want to get into. You want to get into your current limiting dual element time delay fuses. Your class T's, they're built to reduce incident energy. They're built to protect, not the class H's. These are the real workhorses of the fuses. These are your class RK5 rejection. R is for rejection, because they've got the rejection features on them. You know, they're either got these little nubs on the end so that you don't put the wrong fuses in. You put these rejections. You can't put a lower interrupting. You can't put a class H in place of this fuse because it needs to have the slot. The class H does not have a slot on either end, and there's no rejection features on it. So you can't put that fuse into the holder that's designed for these, which gets to that one question. I'm not going to be worried about putting a lower interrupting rating or a lower capability fuse in this because we build in rejection features. Another nice ease of use perspective from a fuse. Dual element time delay, good current limitation, optional fuse indication. So there's a lot of different, you can tell when these fuses have given their life to protect whatever it is that they're there to protect. Feeders and branch circuits, you'll see these on feeders and branch circuits. Again, for motor applications, transformer primaries, green is good. RK5, again, rejection. This is what their trip curve looks like. You'll see, remember, they are a little bit sloped. You know, I like them when they're a little bit sturdy like this, but the reason that gives you a lot of leeway with regard to your motor starts and things of that nature. All right. So this is your RK1. Again, rejection, but you have the ones and the fives, and the one and the five, it'll just you're talking difference in trip curve. So remember the RK5. Remember in your mind the slope of that curve. And when you talk about an RK1, which has a lot of the same stuff, goes up to 300,000 amp interrupting, all the same type of things, but look at what that curve looks a lot different. It's not as sloped. It's a little bit more um, vertical for us, right? But you'll see this on feeders and branch circuits, primary building, electrical, and it's an electrical safety upgrade because, again, if you plotted these things side by side, you're going to cross a little bit further to the left at 0.01 seconds. So you're going to provide better, faster clearing times on lower currents. And that's a good thing. J is for junior. Class J is junior. They're not tiny. They're not large. They are junior. And they go up to 300,000 amps, up to 600 amps, 600 volts. You're not going to get these in 230 or 240 or 300 volts. These are 600 volts, dual element time delay, and fast acting. Feeders and branch circuits is where you'll find these. OEMs and building systems. Type 2, you may not, I didn't put any slides in here on type 2 protection. That is basically that once these things open, if they open, they will provide a case where you don't have damage, you have much less damage inside of that enclosure because they go so fast. Look at the curves. And you'll notice the difference between the fast acting, okay, fast acting, look look at that slope. Look at this is your dual element time delay. You've got a hump in here. You don't have that over here, right? So your fast acting fuses give you, you wouldn't use this fuse on a motor or a transformer primary. Data centers love these fuses. They eat them up. Why? Because they don't give you any room. They don't give you any room for time delay on any of those currents because you don't need it in some of those applications. And then now your class J's, your LPJ as opposed to your JKS, your LPJ is going to give you some time delay, and that is good for your transformer inrush currents, your motor starting. So there was a question about, can you explain real quick why all fuses are not current limiting? And the reason all fuses are not all current limiting is because you have that class H fuse. It's designed for it's just a lower cost fuse when you don't need a current limiting or you're not intended to have a current limiting. It's offered. It's used primarily in your HVAC world and things of that nature. But that fuse, the way it's designed, it's not current limiting in nature. Your other fuses are pretty much all current limiting in nature because it's just the way physics works out and all of the pinch points and how it's constructed. You can always go back. I'm not going to go back for everybody here, but you can go back and take a look at the class H fuse. Class H, how did I end up with this fuse? There you go. There's your class H. How did I end up with this one? The reason you ended up with that one is because you didn't specify a current limiting fuse. There we go. H is how did I end up with this one? All right. I love it. Class CF cube fuse. This one was designed, basically took the class J performance. So if you understand the class J fuse curves, you'll understand the fuse curves for the class CF. They offer a time delay or fast acting. Again, it's a class J performance. Very current limiting, small physical footprint, and the value prop on this one is right here in this panel. We use a lot of these in selective coordination in your Article 700 systems for industrial and commercial power systems. You put this device down close to your load, when the fast acting nature of it makes it really easy to coordinate everything upstream. general purpose fuse. And here's what those two trip curves look like. The fast acting, again, these have the nice hump in them, right? And why do we use that hump? For motors and transformers and things of that nature further up in the system. Our data center worlds love the fast acting nature because we don't have large motors running. We don't have the need to have a time delay. The nature of data centers is get that fault cleared fast. And that's basically what you're getting when you're talking about these two type. There's both in the cube fuse world. One is fast acting. One is a time delay fuse. And then you got your Charlie Chaplins or your control circuits because of that little hat, right? And where do we see these? We see these on your control power transformers, etc. They have that groove ferrule. Again, that's a rejection feature. Very current limiting devices up to 200,000 amp interrupting rating. They're up to 30 amps. They don't go any higher than 30 amps. LPCCs, and again, your time delay offer three different fuse types. You've got a time delay LPCCs, a time delay for motor FNQRs, and then non-time delay KTKs. So, picking the right one. Just remember, if I've got any type of load that's going to draw any type of inrush on startup, like motors and transformers, I'm going to be picking some sort of time delay. If I don't have that, a lighting load, things like that, I'm going to be using a non-time delay fast-acting fuse. And there's your FNQRs. This is your limitrons. Again, that's your fast-acting, or actually time delay fuse. And then here is your fast-acting fuse KTKs. You see how that little beer gut comes down this way, right? And then here is your dual element or your time delay fuse. And again, you have the little hump up here. Okay, you've got it starts out strong, and then it comes in weak, and then it finishes strong. And that is just to let those loads start. And then, we still make those Edison-based fuses. I didn't plot the curves for this one. Didn't see the need to do that. We still have these. You saw these in residential a lot. You saw them sometimes on HVA, or not on dryers. I did open up a dryer one time, and there was one of these fuses inside. Then you have your labels. You're required to put labels on there. You have to have your ampacity, your voltage ratings, whether it's applicable on DC and AC, and your interruptings ratings may be different on DC versus AC. All of your manufacturer, your catalog number information, and then your holders will have to have the same type of labeling on them as well. And you'll notice this one has a cover for finger safe, and then there's an LED right here on the front that tells you when it's open that is the fuse that has given its life to provide the protection to your equipment. Okay. And then the next piece of the puzzle is your let-through curves. So for any of the devices that are current limiting, we have let-through curves. We're required by UL to publish these. We have the table, and we have a curve like this that we're going to show you how it works. And I love this diagram, and I love this because I wish I had this when I was a young engineer. I didn't pay as much attention to that Bussmann SPD as I should have when it came to this. But in any case, this curve tells us a lot. The AB line is basically when there's no current limitation in the picture. This point right here is when it goes into the current limiting region. Any currents below this number will not be in the current limiting region of this fuse. And if I wanted to translate that data point, if I thought about a time current characteristic curve and say my fuse curve looked like this point right here at 0.01 seconds is going to be right in there. That's the point at which it starts to become current limiting. This portion of that curve is basically right in here. And remember, what you got to look at, what you're looking at. You're looking at RMS symmetrical amps across the bottom, instantaneous peak let through. There's no time in this picture. All I know is that I start current limiting at that point and that is when my current gets greater than where it crosses 0.01 seconds. So what does this tell me? My AB line tells me what would be let through if my fuse wasn't in the picture. And that is this top point of the peak short circuit current that would flow in my circuit. Because I have the current limiting fuse in the picture, to know what this new peak is, I go up and over. That's called the up-over method. That gets me this peak value. So I know for a fault current of 86,000 RMS, so it's 86K RMS, for that fault current value, which is right in here, if I don't have a fuse involved, my peak is 198,000 amps. If I have my current limiting fuse in the picture, my peak current is now 49,000 amps. So I took 189,000 amps and I reduced it down to 49,000. And you know what that does? That reduces the magnetic forces in the system. Reducing the peak reduces the magnetic forces in my power distribution system. Now, if I want to know what my new RMS current is, this new waveform, I know that I'm going to clear less than a quarter cycle. I want to know what my new RMS value is. I go up, I hit that line, I go over to the AB line, and I come down. That is called the up, over, down method. And what that tells me is what the RMS value is of this new waveform, because my equipment won't see this whole short circuit current. It's only going to see this little blip of current. And that gives me the new RMS value, which, if I have static equipment like busway, if I have a terminal block or a terminal strip, something that is not dynamic, that is not going to try to open the circuit, then I can compare this RMS value with the SCCR of that busway or that terminal. If it's 10K without a fuse, I need to make sure that my let through, this up, over, and down, gets me to a number less than 10K. If it's 22K, this number has to be less than 22K. I will do that comparison to make sure that I'm providing that level of protection as it's rated. Now, if it's a circuit breaker, I can't do that because a circuit breaker is going to be introducing what they call dynamic impedance. It's going to try to open the circuit, which is going to reduce the short circuit current peaks and whatnot. And now I get into a beast that is not clear cut. That is how we use the up, over, and down method. And that's how I use this table or this chart. I use this chart to determine the peak and determine my let through when I'm trying to determine whether or not I'm going to protect a piece of equipment that is static. And this is basically what that is doing. If I would have a fault current without a non-current limiting device in the picture, I'm going to see that first cycle, at least that one cycle, I'm going to see that. On a circuit breaker, I could have up to 2 to 3, maybe 30 cycles, depending upon the device, the breaker I pick. But that first hump, this is the beast. This is what provides all of the magnetic forces and heat. When I can reduce this peak to something that looks like this, I have less energy, less heat in my system, less magnetic forces than if I let this guy through. I want that. And there's no better demonstration to show that and illustrate this important piece of the pie than to show the cable whip video. Now, what we do in this video is we take a length of 2-aught conductor, and if you've ever felt 2-aught conductor, you'll know it's not very flexible. It's a stiff conductor. I basically put 90 feet of that and I start with 45,000, but because of the impedance of the circuit, I'm really pushing 26,000 amps through this circuit. And what you're going to see is I'm going to let one cycle of current flow through this conductor, and you're going to see the magnetic forces that occur when I let one cycle flow of current. It's 26,000 amps. Get ready for it. Watch closely. Did you see it? There you go. Okay, that is one cycle of current flowing through a 2-aught conductor. And it's very, it leaves an impression, especially if you're in your lab watching it. Now, the results of that is that the first half cycle, the first half cycle was 48.1 kiloamps peak. So 48.1 kiloamps was that data point right there. And what I let so that's the peak. That was the magnetic forces. That's what contribute to flinging that conductor around. The I squared T is the heat, and that has to do with the duration of one cycle. And I let through 15.7 million amp squared seconds. That's a lot of heat. Now, to show what a current limiting device does for us in a power distribution system, we put a 200 amp class RK1 fuse in the picture. The same exact scenario, 26,000 amps, 2-aught conductor, and we do the exact same test, and now you'll see the results of that test. Now, I don't know if you saw that, but watch it again, and I would say watch right in here to see that move, and you'll notice how there is little to no movement in that conductor. And what we've done by the use of the current limiting nature of the fuse, we reduced that peak current, that half cycle, which was 48,000 amps. We reduced it down to 10,000 amps. That's why we didn't see as much magnetic forces on that conductor. And we took the heat from 15.7 million amp squared seconds to 127,000. That's a huge reduction in the heat and the magnetic forces. We basically we have a 1/25th. When you look at the reduction in the peak, it's 1/25th of that peak current. That's how we've reduced that, and the energy is reduced proportionally as well. Now that fuse, when we take it out of the picture of that fuse that I had earlier in my presentation, that was the fuse that was in one of those tests. So before I go on, I'm just going to look comments. Can you explain real quick the fuses? I missed the point earlier. Okay, I already talked to that one. Are fuses now rated 1,000 volts to match the NEC? No, not necessarily. They don't necessarily have to be all moved to 1,000 volts. They moved the code to 1,000 volts, but I don't necessarily need a 1,000 volt fuse. My question, Johnny, would be, where would you use that fuse? Outside of a PV system, we do have 1,000 volt fuses for photovoltaic systems on the DC side. We've got 1,000 volt DC fuses. We've got 600 volt AC fuses, but the demand and the need for a 1,000 volt AC fuse, we're not seeing it. We're not seeing where that's used. If you know or have applications where you need a 1,000 volt AC fuse, we have DC, but if you need a 1,000 volt AC fuse, tell me where you're needing it. where the application is. We're talking about that right now in the fuse standard to increase that to 1,000 volts. But as we're going through this journey, we're asking the question, where would you use it? Okay, let me take a look at the chat sessions on. In New York City, we use Class T fuses on meter bank disconnects to series rate with the apartment breakers. Yes, Joseph. Very good point. Thanks for putting the link for the SPD out there too. And I'm going to take this and I'm going to copy it. And I am going to put that over here, Control V. And then Roger just had a question. Can you explain the current limiting definition? So current limiting is when from a fuse perspective, I am clearing that current less than a half cycle. Sorry, Greater Austin. So I don't have so I'm clearing that I'm clearing that current less than a half of a cycle. I have specific performance requirements on how much I'm permitted to let through, and I'm looking at the standard, and I got to clear that fuse. If you look at the actual definition, and I'm not even going to read it out of the book because you'll be more confused once you read it. But in any case, clearing the fuse, clearing the circuit in less than a half a cycle. Excuse me. Also non-current limiting. Oh, okay. So other manufacturers may have K5 fuses that are non-current limiting. That's true. If I have high short circuit value and I need to reduce the short circuit current, can I use limiting fuse and it will reduce the value without damage? So Muhammad or Mahmoud, yes, you can. If you take a look at the this whole discussion that we just had in this current let through the RMS values, I am able to reduce the RMS, but again, it's how you're going to use it. I could translate this into incident energy reduction. I could translate this into a lot less equipment damage, etc. It's just what is your goal, and if you're trying to increase the short circuit current rating of, say, a piece of equipment that has a circuit breaker in it, I can't use this method. I can, though, say that I've reduced the incident energy and I've reduced the hazard. I just can't increase the short circuit current rating of a piece of equipment that has a circuit breaker inside. But that's this whole discussion and current let through and whatnot that we just had that I think helps you in your journey to understand reducing the short circuit current and reducing the damage. Michael Bayer, the cube fuse are great for UPS fed panel boards where breakers do not work. Yeah, but you can use these in a lot of different applications, UPS areas. That's a good point. 1,000 volt AC fuses. Uh-oh. I don't know what just happened, but my PowerPoint just decided to restart. So I'm going to let PowerPoint start while I look through the chat sessions. And used in railway, 1,000 volt AC fuse is available in SEBA and used in railway applications. Thank you for that application. All right, so my PowerPoint decided to stop and start, which is cool. Thank you, Microsoft, for getting me back up and running without having to do anything. All right, so I am going to go back to the regularly scheduled program. All right, so let's take a look at this. Boom. Now, we talked about the rejection features. You have your Class J fuses and equipment, and only Class J fuses can be installed, and it's because of these rejection capabilities. Either it's the didn't want to do that. Either it's this type of little nub on the end or a slot inside of the blade. That's how we establish the rejection capabilities of those fuses. All right. Okay, so the next step, we'll do a time check. It is 1:37. I wasn't sure if I was going to have time, but I am. I am going to take a look at medium voltage fuses real quick. I'm not going to get through a lot, but I've got at least 20 more minutes for medium voltage. We are going to hit the medium voltage world of fuses. All right, medium voltage fuses. We have current limiting and your E-rated, your R-rated, your PT fuses, and we have expulsion type fuses, boric acid type, and your cutouts. These are what you'll see. Some of these you'll see up on the utility poles, and some of these you will see in your medium voltage equipment. You know, the type of the construction of the fuse is very similar to your low voltage fuses. They're just bigger. You have, in some cases, indication where you'll know whether or not that fuse has opened. The barrels are, you'll have sometimes a single barrel or up to 4 barrels in one unit. You don't want to be putting these in parallel on your own out in the field. Available accessories, you'll have fuse mounting, fuse clips, and things of that nature. UL recognizes the different types of classes, the voltage class. You have your R-rated and your E-rated. They'll determine the voltage ratings, etc. The fuses, the diameters are in the construction. And if you look, remember I talked about the elements inside. They will be. It's hard to tell in here, but in this example, this element is actually coiled something like this. It's doing this basically all the ways around because I need that, because I need so many of those elements in there. You have sand in those just like you have in the low voltage power fuses. And again, you have that helix fuse construction because I need a lot of those pinch points. Silver elements, glass epoxy tube, all that good stuff. The element burns back until there's sufficient gap to interrupt. Basically, that you have the same deal that you have with regard to the low voltage power fuses. You know, that element, you have ferrite or fulgurite, will turn to fulgurite and it'll isolate on short circuits. There's your helical. You can see a nice fuse construction picture in here. And then you have the pop-up that'll give you the indication on whether that fuse is opened. Again, there's standards associated with how long and how that will how far it will protrude, but it doesn't talk about the striker force. Expulsion fuses use boric acid, and this is something you'll see, and you can hear them go off when they go off. The boric acid decomposes, produces a blast of water vapor, and extinguishes the arc. Can't restrike. So again, they do their job. This is sort of how they operate, and you'll see. Basically, you have the amp sizes, and again, because these are medium voltage, they're not six. You're not going to have a 6,000 amp fuse in these medium voltage fuses. They're going to be relatively smaller in their size, and you have that silver element that will melt down on the bottom. You basically have the element, the rod is going to withdraw and elongate the arc, basically letting the boric acid do its job and extinguish it inside of that tube. You'll see these up on poles and the cutouts. You can replace these things. Again, you'll have your current limiting and non-current limiting. And current limiting is very similar with regard to the capabilities of this device. You're going to clear that within a quarter cycle. Non-current limiting device is going to let those cycles flow, and that's a lot of energy and a lot of magnetic forces. And when you look at the two different types of curves, that's where it's all shown right there. You have your non-current limiting fuse and your current limiting fuse. Those are your E-rated fuses. Must open in less than 300 seconds at 200 to 240% of its E rating. And you'll see it's a very fast-acting device, and you'll have your motor starting, so your medium voltage motor startings. This MP3000 is a motor protection relay. A lot of those larger medium voltage relays motors will have relays associated with them. I want to re-show. They wanted me to re-show the internals of a medium voltage fuse. Yeah, I did go through that pretty fast. Sorry about that. So there's your internal. You got a spring. You've got an epoxy tube. You've got a boric acid. Your arcing rod. This is your expulsion type fuse. I'll just walk through this again because I did have somebody out there want to see this again, and I will oblige. That's basically how it works. You can always go back to the YouTube and watch it again. But that's basically how that puppy is working. All right, so and back to this. So there's your medium voltage. When you get into these big motors, they're going to invest in a relay, and then you'll have your medium voltage fuse to help reduce your short circuit damage. Your R rating, again, there's a certain area in these that you don't want to operate. You want to be in a certain region of these fuses. Fuse is going to clear at a range of 15 to 35 seconds at a fault value of 100 times its R rating. That's where that point is on that curve. And this is how you get how you basically preliminarily choose the fuse. You do some simple math and you'll get a ballpark of where your rating needs to be. But you're going to want to check the TCC curve against your motor. And you're going to want to take a look at that, the fuse curve with regard to the overload relay or whatever overload device that you have in that picture. And it has to intersect the fuse above that minimum interrupting rating. So this is sort of the overlay that you want to do on these fuses for medium voltage. You could do your 2.3 kV 100 amp versus a motor. You multiply that, divide that, you get 6.6. That gets you an R rating of where you need to be. There's your overload relay. You're going to want to plot those together. You have your 110% locked rotor amps, your 125% full load. And you could, in between these two, you could pretty much draw your start curve in between those two data points. Okay, and you're just going to want to make sure that you pick a fuse that will let that motor start and you let your overload elements do their job in protecting the thermal capabilities. And there's your E-rated 100 amps. That's basically what she looks like. Those let a lot. This is your medium voltage. You can have these on the primary of a transformer. They'll let through a lot of energy on the secondary of that transformer. This is where you'll see your E-rated and R-rated fuses. And your PT fuses. I'm not going to get through catalog numbers, but there, and when you're picking these fuses, you got to think about the mounting configurations, whether it's bolt-on, clip, and all that good stuff. So, those will all have, those are going to be important parameter points because depending upon the equipment that you're putting it in, will determine the equipment. So, for example, medium voltage metal enclosed switchgear, they'll have a way to mount that equipment depending upon the manufacturer of the equipment. They'll have sometimes their own mounting mechanisms in that equipment. So you're going to want to make sure you match the mounting mechanisms with those installed units. All right, so it's 1:44. What I'm going to do for the last few minutes here, I know we had some questions about the transformer, and what I'm going to do is I'm going to end this slideshow. I'm going to discard my annotations, close that. I do have that open, but I'm not going to show that one. I'm going to bring up my SKM software, and we're going to just do a plot. And while I'm opening that, so can you re-show the internal? Already did that. For low voltage, someone's talking. Check your mics. Yeah, that'll be in order. James, I'm going to get you closed off, James. We don't want to hear about your order. Oh, looks like you found you before I could find you. All right. So thank you, James. All right, so I'm getting SKM up and running. Oh, there's SKM. There's the, see, I was working on this today. There's those fuses. Let's go take a look, and this is my TCC1. This, whoop, use TCC. This was my motor starting. So we'll just, but basically what we'll do is we're going to create a new one, call it XFMR. And we're going to add a transformer in. And we're going to say that, I don't know, we'll say it's a 1500 kVA transformer. And we'll say 4160 primary. And we'll say 480 secondary. Bus voltage on the primary is 4160. And since I'm just going straight into this, I'll have to enter. A lot of times your bus will automatically populate that. And there's your transformer damage curve. I'll do this times 1. So there's my damage curve. Percent Z. I got to give it a percent Z. I don't know. 5.75 sound good to everybody? I'll change that to about 6. Hit redraw. Okay, so there's my transformer damage curve. 2 winding transformers. And then what I will do is, let's see. Need my calculator. Anybody out there want to hazard a guess for a primary fuse size? What would you pick? So I got 1500 kVA. Divide that by 4.16. Divide that by 3. Multiply that by square root of 3. 208 amps on the primary. Sound about right? Okay, so let's take a look at adding a fuse. Okay, so let's say 4160, 4160. We pick the library. We go to our library of fuses, and let's pick a busman maybe. No. We're worried about this this here. This just doesn't do it right. Let's pick a busman. Okay. Yeah, 60, 260. Let's take a look at different types, different size fuses. Okay, 750. Can't get that. That's way too big. Hold on. Go back to the library. All right, so, and somebody had mentioned earlier about providing too much of this. So let's just talk about that. This portion of the damage. Think about on a primary, on that fuse that's on the primary of the transformer is going to be there for short circuit protection of that transformer. Your secondary devices, your secondary main overcurrent protective device is going to limit the amount of load that you put on this transformer. So if I had, this is a 1500 kVA transformer, divide that by 0.48, multiply that, divide that by 3, multiply that by 3 square root, and 1804. So you're at an 1800. So if I looked at the secondary, let's add a secondary fuse, low voltage fuse. I would probably have a class L fuse there. So we're going to give it a voltage rating 480. And I'm doing this on the fly with regard to, I'm not building a one-line diagram and all that jazz. So I'm going to pick a class L fuse, and I'm going to be around 1800 amps or so. 1800, 1800. Pass it up, class L. Here we go. There's my KTUs, KRP in Cincinnati, KRPCs. All right, so 1800, right? So let's say I picked 1800 amp fuse. This is on the secondary. I could go with a smaller fuse. I can go with that fuse, but your your upper portion of the damage curve on a transformer really is the long time persistent overloads, which is going to be protected by your downstream overcurrent protective device, not letting more current flow through the transformer. But again, you have to pick your primary overcurrent devices based upon, depending upon which portion of this, and we could go into the damage curves for transformers and the IEEE C30. I think it's 3C37 or whatever. You have a specific fuse for competitor's product. Isn't Limit Amp and GE ABB trademark? I'm not sure if Limit Amp. Let's go back to the library. Let's take a look at what GE has on here. I'm not familiar with their curves. So I'm not as familiar with the GE. Let's try ABB. ABB curve, medium voltage with the CEF fuses. And it's not going to cut it. What the heck? Let me go back to the library. What the heck am I doing? 100, 130, 550, 65s, 1200 voltage, 15. That's definitely not going to work. But just looking at the different characteristics, see, their fuses are similar. They'll have the different characteristics on these strip curves. So you got ABB, another fuse manufacturer. You've got your Kearney's. S&C is another popular brand. So there's your, again, your different types of E's and whatnot. So just take a look at very slow speed. What do they mean by look at see how that is. That one will curve in across and give you some additional protection on this transformer as well. So on the medium voltage side, you're picking a device, but you don't have to worry about this upper portion of that transformer damage curve, because that's your primary fuse that you're going to be using is more for the short circuit protection capabilities than it is for the overload on that transformer. So you're not necessarily worried about that upper portion. You're more worried about the capabilities of the short circuit nature of that fuse. Anyway, so that's basically what I just at least wanted to show you that damage curve and all the different options that are available in all the different, you have the different voltage classes, so wouldn't need to go up that high on those specific voltages, for a 4160 type of application. But again, you're worried about this transformer inrush. You don't want to open that fuse on the primary. The primary fuse usually is going to have something that's very sloped at the bottom. So that's basically what you're working with. And you got a lot of different options to pick that primary fuse. All right. Enough of that. We are 155. I just at least wanted to look into the transformer primary. I didn't get into picking all the different fuses and whatnot, but that just gives you an idea. Primary and secondary fuses are working together. The primary fuse is going to give you that short circuit protection. That secondary fuse is going to give you your overload type of protection. All right. I'm looking for my chat box. Oh, there it is. And I'm going to scroll down, make sure I got that. At the meantime, I'm going to 64 is what you want. Write that in. If anybody asks for it, just remember that. These ratio tables, what this means is if I have a downstream fuse and an upstream fuse, as long as, for example, if I have this TCF fuse, that's downstream of, say I have this TCF fuse, 30 amp downstream of, I don't know, an LPS, as long as I maintain a 2-to-1 ratio. So if I have a 30 amp TCF downstream of anything that is 60 amps or more, I maintain selective coordination for all currents up to 200,000 amps that flows through them. So 2-to-1 ratio gets me, as long as I have a 30 amp downstream of a 60 amp or greater, I maintain a 2-to-1 ratio. I selectively coordinate. I have a video on my YouTube that goes over these tables and how to use them, and I go over transformers, selecting them on the secondary and primary of a transformer to properly use these tables. These are very important pieces of the pie. Hopefully that gets you there. Thanks, Gabe, for publishing Dan's Mentomy or Dan's program. I'm going to remind you, 12/23/64. I too would love to hop on to Dan's thing. And Ken, thank you very much. Thanks everybody for dialing in. And for those on YouTube, I am going to start to play the outro because that's what we do in this program. We have an intro, we have an outro, and I'm going to cue up the outro right now. Thanks for joining us. Don't forget to hop on over to Dan Carnevale's program. Thanks for joining for this 2 hours on fuses. I hope you got something out of it. Remember to subscribe to my channel. Take care, God bless, stay healthy, and stay safe.